Okay, welcome to today's webinar. Today we're going to be talking about machine safety and specifically how to conduct effective hazard and risk assessments for machinery applications. I'm Chris O'Brien and I'm a partner with Exida. I work with our customers, both OEM customers who design equipment and end user customers who take that equipment and use that in their plants and facilities, and help them on meeting the functional safety standards, as well as making sure their systems are installed and operating in a safe way. Today, our webinar, we're going to look at hazard analysis, risk assessment, and safety requirements. So primarily the analysis phase of a safety life cycle. We'll look at the requirements and guidance given by IEC 62061 and ISO 13849, and also look a little bit broader into general guidance in the industry. We'll look at techniques for determining how much risk reduction is needed, and we'll look at different methodologies that could be categorized as qualitative, semi-quantitative, and quantitative to do risk determination or SIL determination. And then we'll wrap up by talking about what information should be captured and stored in a safety requirement specification. Now, this webinar is going to be the first of three. It'll be focused on the analysis phase and the application to machinery. We'll follow that up with one on designing safety-related control functions and installing them, and then finally we'll have one on maintaining and keeping safety-related control functions and safety systems in good operating order so you are achieving the risk reduction you need. A little background about Exida. We're the leading global functional safety consulting firm. We do functional safety consulting and certification. We've got offices throughout the world and over 120 experts to help our customers with their safety and reliability needs. Some of our key things we provide are consulting, product certification, training classes, engineering tools, reference materials, and professional certification, competency testing and certification for professionals. One of our key tools, or one tool that a lot of the industry uses, is Excellentia, which is a integrated lifecycle tool that will help do the risk assessment, do the conceptual design and documentation, and even record data over the life of a plant. It's built up of a series of best-in-class tools, and you can use all of them or just the ones that you need for your specific part of the project. And we'll take a little bit of a look today on the FACTS tool and the LOPA tool. We'll do an example of risk assessment using those tools. And as I mentioned, you could use individual tools, or you can integrate them overall and do an entire project with them, which has some significant benefits. We publish a lot of reference books. We write and publish our techniques and methodologies. This is all part of our mission of helping to contribute to the science of safety and reliability, and it serves as a good way to communicate and share our knowledge. All right, well, so today we're going to take a look at basically the analysis phase and how that applies to machinery. So I'd like to start by reviewing what is risk, talk about safety life cycles as they're shown in different standards, and then we'll dig into hazard analysis, talk about tolerable risk, which is a topic I often find that in machine applications is not that well defined. Then we'll look at different risk assessment techniques, and again, wrap it up with what should be captured in a safety requirement specification, and then we should have time for questions and discussion at the end. So the first thing that we've always got to start with is, what is risk? So risk is the measure of likelihood and consequence of an adverse effect. So basically, how often could it happen and how bad would it be? So in machinery, we're looking at often risks that could be cuts, bruises, amputations, and up to fatality. So that's how bad it could be. And to understand the risk associated with a machine or a process, we need to understand what the consequence could be, but also how frequently that could happen. Risk can be allocated or evaluated against multiple risk receptors. And you could think of those as ways or categories under which you could group your risk. So the three most common that we see are personal safety, environmental impact, and financial loss. Typically, everyone who is going through one of these safety life cycles is at least going to be looking at personal injury or fatality, and then often environmental and financial. But there can be other risk receptors, or there are other risk receptors, such as business interruption or company image or loss of market share, that risk targeting can be done against those receptors. How much risk against consequences that fall into those categories? Or excuse me, what's the likelihood against consequences that fall into those categories to get the risk? When we're looking at safety-related control functions, so if we were in the process industry, we'd be talking about safety instrumented functions. The terminology for machine safety is safety-related control function, or safety-related part of the electrical control system is how 13849 discusses it, but we're going to use the terminology out of IEC 62061, understanding that there are similar phrases that might be used in ISO 13849. But if we were looking at, first thing we want to understand is the risk, and then understand, do we need to go to some type of automated system to protect it? So we start with the machine risk, then we can look at ways to reduce the risk. Maybe we could have a change to the machine to make it inherently safer. Maybe there are designs or access we could put in place. We could put particular controls in place, alarmings, guarding, all of that could reduce the risk, but we still may be above our tolerable risk. And if we are, then we would implement a safety-related control function to get below our tolerable risk. And we're going to dig into tolerable risk because, as I mentioned, that's an area that in machine applications often isn't well defined or well understood. There's different places we can get indication of what is tolerable risk. ALARP is a principle as low as reasonably practical, and for example, the Health and Safety Executive in the UK puts out guidance as to what is unacceptable. So here they would say intolerable would be 1 fatality per 1,000 years per worker in a plant, or 1 fatality per 10,000 years for somebody outside the plant. Under no situations would that be acceptable. To a broadly acceptable region, which is if the fatality frequency is less than 1 fatality per million years, then that would be considered acceptable. In between those two numbers is an area that's considered as low as reasonably practical if it's worth it. So there might be situations where you can't practically drive the risk low enough to meet the 1 in a million years target, but there might still be a reason to operate the plant or machinery in the range between 1 fatality per 1,000 years and 1 fatality per million years. So that's a public document that's useful and can build consensus around targets for tolerable risk. Other things that inform tolerable risk are what is the actual fatality rate or injury rate in different industries. So this is from a National Safety Council study for the US, and here you can see total injuries by type, total injuries and injuries by type, and those that happen in society and those that happen in industry. And then you could look at the number of people employed in industry and the number of, say, amputations, and you could then say, okay, well, we've got this is the industry rate. We want to be 5 times better or 10 times better or 100 times better than that, and that could help inform how to set a risk target. Similar data, this is data from Australia and UK, and this is fatalities by different industries. So you can see mining and quarrying is particularly dangerous. And this is a fatality rate per million years in the industry. So there is data out there, and that can be gathered and used to inform a company in setting their tolerable risk guidelines. So we talked about risk, and now we're going to take a look at a safety life cycle and what's the purpose of a life cycle. So the purpose of the safety life cycle is to build safer systems, eliminate repeating mistakes of the past, make the systems more cost effective, and aligning the cost of the system or the reliability of the system with the risk it's mitigating. So for example, you don't want to put a very reliable, you wouldn't want to consider putting a very reliable system on a low risk application and then not putting any system on a high risk application. We want to eliminate weak links in the design, so we want to take things out of the design that aren't really adding or doing anything to increase the safety. These safety life cycles do provide a global framework, so now there's kind of a way for organizations organizations to talk to their suppliers or global organizations to work in multiple countries and design to standards that are internationally recognized. And also very importantly is they require and they set up a way to look at what's actually going on with the systems and provide feedback on that performance, both to the users and to OEMs. First life cycle we're going to look at is IEC 61508. So for the modern functional safety standards, IEC 61508 is the umbrella standard, is kind of the first one that introduced a lot of new concepts. It is generic in that it's not, say, written particularly for the machinery industry, but it does follow a flow that lays out the steps that should be taken. So we need to do an analysis of the risk, we need to design and implement a system to mitigate that risk, and then we need to operate and maintain that over the life of the machine. IEC 62061 has similar steps that aren't necessarily structured in a life cycle, or they don't use a life cycle drawing, but we can create one. And there's collect information on the machine use, do a risk assessment, determine if any safety-related control functions are needed, write the SRS for those control functions or the control systems. That's the analysis phase. That's what we'll be talking about today. Design and implement that system, integrate it, integrate it, test it, install it so it's ready to run. That's the realization phase. And then you're going to operate and maintain that over the life of the machine. There's a life cycle similar to the 61508 life cycle, and there's general requirements for the management of functional safety. I will say both IEC 62061 and ISO 13849 I feel are weaker on the safety lifecycle requirements than, say, IEC 61508 would direct. So we think it's important to look at the requirements within these machine-specific standards, but also then broaden the view to say, is this a robust life cycle, or what other things should we borrow from 61508 or a parallel standard as IEC 61511, which is a better, more well-defined life cycle for operations and maintenance and the whole everything you need to consider. So this is a good example. So IEC 62061 connects with different standards. So general guidance on risk assessments for machines are given by standards such as ISO 12100, 12,001 100 or ISO 14121, they give general guidance. The machinery safety standards are focused more on when you get to the SIL determination and then how do you design a system, and they have a little bit of, very little description of operation and maintenance phases. But this shows where you can find these ISO standards for risk assessment. Use 62061 in here for the design of a safety-related electronic control system. And at some point, you might even go to 13849 for simple systems. And that shows a correlation. If we look at 13849, that also has a safety lifecycle flow. In the analysis phase, we have similar steps: determine the limits of machinery, hazard identification, risk estimation, risk evaluation, and determining do we need a safety-related control function. If we've met our risk and it's been reduced adequately, then we're done. If not, we're going to come over here and say, and we'll touch on this a few times, could we have an inherently safer design? Could we use safeguards? Information use is not preferred over an automated system, but it's another method. And then we can kind of see here that if it's a simple function, we might use 13849. If it's a complex function using a programmable electronic system, we would probably want to look at 62061 as the guidance for that. And then these will be for future webinars, but basically then we've got our conceptual design and realization phase, and then we're going to install and operate it, similar to 62061. Now let's back up to that hazard analysis. So ISO 12100 is a good standard for that, or is the guiding standard in machinery for that. And we're going to have hazard identification and evaluation. And if we've properly mitigated, then we're done. We're going to document it. If not, this is an important little flow because it gives you a priority of methodology. So the first thing is, could you reduce the hazard? Could you remove it? If you can, you should do that. If not, could you reduce it by having inherently safe design measures? If you can, you should do that. If not, then we're going to take a look at using guards and protective devices, so safeguarding and safety-related control functions. And then finally, if we don't get that, that's where we're going to do informative and information, signage and other things to warn people of the hazard. But ideally, we reduce the hazard in the machine, then we add safeguards and active functions, and then if we can't, we're gonna have to do it with signage. Oh well, here's a good clarification from somebody on it. I appreciate it that 14121 was rolled into ISO 12100. So that's a good note. So thank you for that clarification. So we're doing our hazard assessment. So typical requirements for a process hazard assessment or machine hazard assessment are: what are the hazards associated with the machine? Are there previous incidents with severe or catastrophic potentials? What are engineering and administrative controls on the machine? What happens if those controls don't work? What is the siting, specifically layout, access, and exposure? What human factors do we need to consider? And a qualitative evaluation of the effects of the failures. So we want to look at those typical requirements. We want to look at then considering those requirements within typical techniques. So common techniques that can be used for process hazard analysis: checklist, what if, combination of what if and a checklist, hazards and operability study, failure modes effect analysis, and a fault tree analysis. So depending on the complexity and the novelty of the machine, you might pick a different technique. Often a starting point is checklist, and there are machine-specific standards that list hazards that should be concerned. There are, so if we look at checklists specifically, the strengths are their simplicity. There's many checklists available from different sources. Weaknesses, and something that we're seeing more and more is we're getting more novel machines, and specifically maybe more automatic guided vehicles, more robotics. Available checklists do not necessarily cover all the hazards specific to the machinery, and they may not provide enough guidance. OSHA has checklists. Royal Society for the Prevention of Accidents also has a checklist. OSHA's got one that's downloadable from their website. So those are a very good start, and a very good start for doing, your base start for a checklist. Here's an example from an ANSI standard that's giving different significant hazards and sources of hazards this is for a turning machine. These would be things to be considered, and you've got multiple different examples of these. So these are things that we should use as the beginning of our hazard analysis, but may not be exclusive. So as I mentioned, we will find that we're going to have maybe not complete coverage with a checklist approach when we go to novel machines, automatic guided vehicles, robotics. So there are different techniques such as a HAZOP, which is going to use guide words, and those guide words can be found in the ISO 12100 standard. It gives you guide words for machinery, so there's a good basis of what to start with. So if we're looking at hazard and risk assessment, what are the hazardous and hazardous events of the equipment? What sequence of events lead up to that hazardous event? What machine risks are associated with the hazardous? Any requirements for risk reduction? Are safety functions needed? And are any of those safety functions safety instrumented functions or safety related control functions? Now, when we're evaluating risk, the risk reduction required is the difference between the machine risk and the tolerable risk. So the machine risk is the inherent risk associated with the operation of the machine. The tolerable risk is the risk that the organization has determined it can tolerate or accept. Then the necessary risk reduction is the gap between the risk you have and what you need to get to. So how do you know if you get the risk low enough? It's low enough if it can be determined to be negligible, then yes, it would be considered low enough. If the risk is in that as low as reasonably practical, then additional safeguards should be considered. We could say on a cost versus risk reduction benefit basis, some countries are going to say you're not going to be allowed to run if you don't get it to the tolerable level. And there's a cost, not just equipment cost or operating cost, but sometimes as protective functions get more complex, they become reliable from a safety perspective, but the machine becomes unavailable, and often that can lead to bypassing or defeating the safety functions. If the risk is in the intolerable level, then again, it must be reduced in order to operate. So we touched on these. Ideally, we can eliminate the hazard. We can add safeguards. ANSI B11.6 kind of gives this list or this sequence. Again, eliminate the hazard, control exposure by guards and safeguarding, provide other safeguarding such as awareness barrier, signage, and then finally administrative controls. Now, why do we need to specify a tolerable risk? Because if we're going to determine how much risk reduction we need, if we're going to tolerate the risk reduction we need to know what our target is. And to do that, we have to not understand just the risk associated with the machine. So again, risk would be the consequence and the frequency, but also the risk reduction then is that unmitigated risk compared to the tolerable risk. So if we don't specify tolerable risk, we can't determine a risk reduction factor. So if someone were to say, well, I can't tolerate any risk, well, then our tolerable risk is 0, and regardless of, unless there's absolutely no risk associated with the machinery and equipment, you're never going to be able to reach an infinite risk reduction. So this is an important concept that we often find isn't maybe explicitly articulated by the companies doing it. So when we define a tolerable risk, there's things to consider. We need to have a rigorous process. We need to consider all relevant forms of harm. Needs to be consistent with company and society practices. We're going to use that to get the SIL target. And the way we specify that tolerable risk is going to define how we do SIL selection. And this can be a difficult process. This is the ALARP drawing again, but it does give indications, say in the UK, what the Health and Safety Executive has put out as tolerable risk examples. There are other countries that do that. So in Australia, they have a tolerable risk guidance for the use of the land or what the type of facility is. We can look at industry accidents to see how bad certain things could be. These happen to be process industry, but they tend to be bigger and have kind of more dramatic accidents. We can look at general statistics as to risks of dying or risks of other things happening. And for example, you could this is an example of defining tolerable risks. So an organization could say, hey, we want 0.0005 fatal accidents per person per year. We want 0.005 injuries per person per year. 0.01 significant environmental release per plant. 500,000 in business loss. So those are examples of tolerable risk guidances that could be set up. But there are some things that are good and some things that are bad with that. So what's good is it uses precise numbers and addresses health and safety, environmental, and economic loss. A bad attribute of this might be that the numbers might be unrealistically precise, and we don't know the number of people in the plant or the number of plants. So these tend to be things that are evolved or worked over time and refined. Now, once we start setting up those tolerable risk guidelines, we can create a risk matrix where we could look at the severity of the event and the frequency of the event, and kind of define, is it acceptable, moderate, or extreme risk? And you could see as the consequence becomes greater and the frequency becomes more frequently, those become more extreme, and less severe consequences and more or less frequency become acceptable. So that's kind of just a general way these grids are set up. Then when we've got that, we can look at that. When we have our tolerable risk, now we can do our risk assessment or our SIL assignment. So how are we going to do that? We're going to look at a couple methods. The purpose of the SIL assessment or performance level determination is we want to document how effective the control function needs to be. There are qualitative methods, and those are kind of broader. I won't say they're subjective, but they're more qualitative terms like we just looked at. Once in 100 years or once in 10,000 years with a general category of harm. Quantitative methods are going to give you more specific risk target numbers. So in qualitative, we're going to basically have order of magnitude targeting, and in quantitative, we're going to get more precise. Want to use a consistent method or selection of methods to evaluate risk, and you want to kind of get that into your organization and use the same thing over time. Now, we're going to essentially be calculating or determining how much risk reduction or probability of failure over a period of time we need, and that's going to relate to a SIL target. So for high demand or continuous functions in IEC 61508, and we'll take a look in a moment in 62061, but the graph is going to be the same. It's going to give a range of probabilities of failure per hour to meet a given SIL level. So the higher the SIL level, the more risk reduction you need, the lower probability of dangerous failures you can tolerate. There's different modes of operation that a system can be in. There can be a demand mode or a low demand mode where the protective function runs for years, and it might only be called upon to work once a year, once every 2 years, at a very infrequent period. In those types of systems, you can do periodic testing, and you can also then take credit for diagnostic functions. In a high demand mode, you are going to be not taking, that's where maybe every couple hours or once a day or once every couple days that protective function needs to work. So if you did a periodic maintenance and testing once a year, you wouldn't take credit for that in a high demand application, but you would take credit for automatic diagnostics if they basically de-energized the machine or brought it to a safe state. So many machinery applications are high demand. A continuous mode is basically when the failure of the protective function is going to cause the hazard or you're immediately at risk when it happens. So an example of that would be your power assist steering in your automobile. If that system fails while you're driving 60 miles an hour and it gives you torque assist on the steering wheel like it would in the parking lot, that would cause a hazard. Or another automotive example would be that power assist steering, electronic power steering, in a maintenance mode. So if the car is on a lift and there's a mechanic in there working inside the wheel well and that wheel turns, that failure causes the hazard. So that would be a continuous application where we wouldn't take credit for diagnostics. We have a couple questions. How do we categorize? Oh, I think we're getting to some of them. How do we categorize demand mode versus high demand? So demand mode, I think we just covered that, so hopefully we answered that. And there's a question about alarms. when to consider them. So we'll dig into a LOPA. We'll dig into the LOPA a little bit deeper in a few moments, but alarms. That LOPA diagram was basically, you often do the LOPA to determine, well, you do the LOPA to determine how much risk reduction you need for the safety-related control function. The order in the LOPA doesn't necessarily mean the order that the protective function would actuate. So you might have a control function first, then a safety-related control function, and then an alarm. Might be the actual order in which you set up the machine to work, or the precedence of priority you give things. But when we're doing that LOPA calculation, we're actually trying to calculate how effective everything else is to determine how good our safety-related control function needs to be. So then we look at 62061, and that only goes to SIL 3. It doesn't go to SIL 4. So both demand mode, which is that low demand where we're looking at, the standard does say a demand greater than once per year, but that's not, there are some stuff in the standard where they talk about the different modes that we would say really should be used more informatively, because if you had a demand once every 11 months, but you did proof testing once every 3 months, you should model that with a probability of failure on demand calculation, not necessarily a high demand application. And then the difference between continuous and demand is more how effective are the diagnostics. So essentially, if you've got diagnostics that run once a day and you have a demand once an hour, well, you say, well, those diagnostics aren't going to tell me, aren't going to operate quickly enough to bring the system to a safe state, so I'm not going to count on them. But conversely, you know, there's a rule of thumb that the diagnostics should run 100 times faster than the demand. But even if the diagnostics are running 10 times faster than the demand, they're providing some benefit. And we've got a couple white papers that go into both assigning things as low demand versus high demand, and then how to treat diagnostic functions when maybe you don't meet that 100 times faster than the demand rate. So there's wording in the standard that would make it very black and white, but the actual reliability analysis, you know, there's gray areas about better techniques to use. So there's a couple questions that are popping up on that, so we can follow up that separately. ISO 13849 gives performance levels with average probabilities of failure per hour, and you can see that there's not an exact lineup with the SIL tables, but we can correlate them. In addition to the performance levels, they've got categories which are going to define, are going to be taken into account with the failure rates, and depending on the failure rates of the device, the category, which is the architecture, we're going to be able to achieve different performance levels. So in 13849, it tries, I would describe it as it's driving to the same overall control function reliability or safety function reliability, but trying to do it in a simplified manner where if your failure rates fall into this range and your architecture is this, then you meet this category. And even as you read the standard, it has notes that saying, you know, calculations were done to validate and set up these ranges. We at exida kind of think it is just simpler to do the calculations, which would be the approach of IEC 62061. But in 13849, shows the categories. Again, categories are the selection of the components and the redundancy, and then it also talks about the diagnostic coverage achieved there, and then this 1, 2, 3 are what's the mean time to fail dangerous, which is the inverse of the failure rate. So if we look, say over here, if we have a high mean time to fail dangerous, which would be a low failure rate, and we use a category 3 architecture with medium diagnostics, we're going to achieve somewhere between, a D to an E. If we use a category 4 architecture, then we're going to achieve an E. And likewise, if we used this category 3 with medium diagnostic coverage, but we had a low mean time to fail dangerous or a high failure rate, we are only achieving somewhere between a B and a C. So it gives guidance, but it is it's semi-quantitative in the approach. So let's take a look at the two techniques that are shown in the standard. Well, we want to look at 3 techniques. Want to go through the guidance in 62061, the guidance in 13849, and then also look at a LOPA example. Now, in both 62061 and 13849, they give, which are informative sections of the standards, they demonstrate a technique for determining SIL level or performance level. Buried into these examples is a tolerable risk criteria. So many organizations look at the standard, go to the back, look at the technique and apply it, and don't necessarily understand that they're accepting an inferred risk tolerance by using these techniques. And again, I point out that they're in an informative section, so they're not in the normative section of the standard, so they're not required. They're very beneficial to show examples, but they're not normative. So we're going to have the risk associated with the identified hazard is going to be the severity and essentially the frequency. So here we've got a frequency of the exposure times a probability times a probability. So we're going to get the probability of occurrence of that harm. So risk is severity and probability of occurrence. So that's consistent with what risk is. So they're talking about probability, but we're really determining a frequency or likelihood. It gives tables to categorize severity, and we go between 1 and 4, where 1 being the minimum, an event that requires first aid, to going to 4, which is irreversible, resulting in either death or the loss of an arm or eye. And 2 and 3 are scaled in between there. We've got frequency and duration of exposure. Again, the standard gives us a table with events 1 to 5. 5 is very frequent, going to be exposed to it more than on an hourly basis. 2 is the least frequent, less than once per year, with some gradations in between there. Probability of occurrence, so how likely is it that this will occur? So specified and foreseeable characteristics of human behavior. We can look at stress, lack of awareness. Again, a range between negligible and very high. And then finally, probability of avoiding or limiting the hazard. Is it possible that if somebody gets into this dangerous situation, they can avoid it? That would be low. If it's impossible, that would be high. Again, a 5. The higher the rating, the more the more risk associated with it. Then we're going to basically determine the class of the probable harm. So essentially, we're going to look at the severity, and then we're going to add up the numbers from those tables for the frequency, probability, and avoidability. And we're going to, the standard gives a matrix showing given severity against the class and what SIL level the risk protection needs to be. So we could take an example where we have a turning machine, and we're going to use, and we've identified two potential initiating event: operator error, where the operator opens the hood while the machine's running, or a second one would be a control failure that leads to an unexpected startup. Now, for time reasons, we're just going to look at item 1. So let's determine they open it. If the operator's hands are near the workpiece, it's likely they're going to have severe lacerations or a loss of a finger. From experience, it's known that an operator will open the machine several times per year while it's running. Even if the protective hood is open, the operator doesn't always reach into the work area. So we kind of know that from our hazard and risk assessment. So now we want to take a look at doing the targeting. So here we're going to take and just basically fill this table out based on how we answered those questions. So since it's potential, laceration or loss of finger, we're going to take the loss of finger, which gives us a severity of 3. We know that they do it several times per year, so less frequently than once every 2 weeks, but more frequently than once per year. That gives us a 3 for frequency and duration. What's the possibility of them reaching in? So we're going to use this probability of occurrence. We're going to say, well, even though they open it, they don't always reach in. So it's not 0 and it's not every time, but we're going to say it's possible. We'll give it a 3. And if they reach into that machine and it didn't turn off and it's running, then the probability of avoiding the harm is nearly impossible, I would say. The mitigation is they don't reach in, which we're going to give credit for, but if they do reach in, they've got a big workpiece in there that's spinning around, they're going to have an injury. So that would give us a severity 3, and we would add up the class to get to 11, and we go over here and we say, okay, severity 3, class 11 to 13, well, that would tell us it's a SIL 2. So that would be using the informative part of 62061. That would be how we target that risk scenario. We can then look at 13849. It provides a risk graphic methodology in an informative example, and it talks about severity of injury. It gives us 2 things: bruising and lacerations without complications is S1, S2 is amputations or death. Frequency and exposure. You can say infrequent if it doesn't exceed 1/20th of the overall operating time, and or not higher than once per 15 minutes. Excuse me. Can be used if the accumulated exposure time does not exceed 1/20th of the operating time. Excuse me. It's not higher, it doesn't occur more than once per 15 minutes, and you should use F2 if frequently or continuously exposed to the hazard. Probability of avoiding it, again, it gives us guidance. P1 if it's realistic to avoid it, P2 if it's not realistic, you should select P2. And now we've got our risk graph. So we've got severity, frequency, and probability of avoiding, and we're going to go through that, and we're going to get our target performance level. So again, looking at the same example, it's a serious injury because it could lead to an amputation. The exposure is seldom or short. It's less than 1/20th at a time. It's not once per 15 minutes. And then the one area that might be a point of discussion for the team would be, is it avoidable or is it unavoidable? So it's one of those things like, well, if they reach in, it's probably unavoidable, but they don't always reach in, so it's avoidable. So you could have I could see two different teams, and another comment that was made is that these risk assessments are done by teams. They're not abstract things, research projects. They're done by people with expertise in safety in the plant, in the operators who use the machine, people knowledgeable about the machines, people knowledgeable about general industry techniques. So you're going to be discussing this as a team, but then I could see a team scoring it either a P1 or a P2, which would lead to a C or a D. So P1, operator will not always put their hands in the work area. Someone else could argue, well, we made it not frequent, so we already included that when we said it was infrequent versus frequent. But this might be something that as you develop company guidelines, you can provide guidance or techniques on, or clarification on how you want to treat that within your organization. So did we get different results? Well, we got a SIL 2 from 62061, and we got a C or a D, depending on how we solved it. So if we did a D, that lines up exactly with SIL 2, and C is just underneath that. So we've got reasonably good correlation. However, the thing I just want to stress is there's an implied tolerable risk guideline in both the 62061 methodology and 13849 methodology. So another quantitative way to do this is a layer of protection analysis. And I would say that both of the techniques we just looked at are semi-quantitative approaches. Each of those decisions or things we took credit for are essentially pseudo layers of protection. So a layer of protection is basically can be done semi-quantitatively, and so semi-quantitatively it was, for example, you might determine specific protection layers you're going to allow the team to take credit for, and you may do them on an order of magnitude approach. A quantitative technique is, hey, we're going to calculate the effectiveness of our alarms and the effectiveness of our training and the effectiveness of each thing we would take credit for. And then we're going to put those specific numbers in and solve it that way. So here's an example if we were talking about an airbag, different things that might happen. So we could have a normal control layer, we could have a safety layer, we could have passive layers. So this was kind of to model a crash of a car. If we look at just building a layer of protection, it's a variation of an event tree, and there are specific rules we use. Like an event tree, the initiating event starts everything going. We take a branch any place we have a layer of protection, and we're really just worried about, we're trying to solve the frequency for one outcome, and that's failure or that an incident does occur. To the question asked earlier, typically the potential SIF isn't included because we're trying to calculate that reliability. Now, also, this is when we look at specifically in 62061, it talks about the SIL determination and references the annex in the back, but it also references Part 5 of IEC 61508 to say you can look there for other methodologies. So when we look into 508, 61508 and other standards, we're going to find maybe a little more robust SIL determination methodology. Oh, I'm sorry, I just saw a question I should have answered sooner. I'm going to back up real quick. Question was, how do you determine the class? The class is determined by adding up these three numbers: frequency, probability, and avoidability. And so 3 plus 3 plus 5 gives us our 11. So sorry, I missed that earlier. I just want to make sure I touched that, got that question. So we're going to have an initiating event, independent protection layer 1, 2, 3, et cetera, each one of those protective layers is going to reduce the probability that the hazard propagates. To be a protection layer, it needs to be specific, independent, dependable, and auditable. So it must be specific in that it's designed to protect against the hazard, independent from either the initiating event or other protective layers. And this can be an issue in machine design where you might have a controller that's controlling the machine and also has safeguards in it. There's a lack of independence between that control function, which could be the initiating event. Say it overspeeds, it loses control function, now it's overspeeding the turning machine. If you're going to have a high speed sensor going into the same controller, the safety standards are going to say, well, you don't have independence and you're not going to be able to claim that. So independence from initiating events or other protective layers are important. A dependable, meaning it must be capable of providing the risk reduction we're taking credit for, and there are systematic issues such as the software and things like that, and random, which would be more component failures, and auditable. It must be testable and maintained over the life of the machine. As I mentioned, that they're built into those informative parts of ISO 13849 and 62061. So severity of injury, you know, is a conditional modifier or layer of protection. Frequency of exposure, possibility of avoiding harm. Those two are classic layers of protection. 62061 also has a severity, then it's got frequency and duration of exposure, probability of that it's going to occur, and probability of avoiding it. So I will say they're pseudo protective layers, independent protection layers built into both of those techniques, which only makes sense. I mean, those simplified techniques are supposed to facilitate doing it, but they should be considering good practice. So we're going to get an incident frequency multiplied by the layers of protection. To do it well, we're going to need initiating event frequencies and probability of failure data. So we could create a LOPA diagram where we have an initiating event times the probability that layer 1 fails, times the probability of layer 2 fails, times the probability of layer 3, and we're going to get an accident as an outcome. So we go back to our same example and we take those things. So let's say operator opens the hoods, it said several times a year, so we'll say 4 times per year. Operator may not reach in. It's not unusual to take a 1 in 10 failure rate for operator making a mistake. Some people would argue they already made a mistake by opening the hood, but they're well trained, so maybe they're just trying to get a better view. And then protection layer 2, they may not be injured. We discussed that we weren't going to give that any credit. And here we would say, here's our 4 times per year times operator doesn't reach in, 0.1, but the operator would be injured, isn't injured, we're not taking any credit for. And so now we have, 0.4 times per year, or every 2.5 years, we get an injury without any additional safeguards. Now, here's an example of a tolerable risk selection that you would need to do. If you're doing a LOPA, you're going to need to write out those numbers. So here we've got severe injury. That way we've set this up, and again, it's an example, could have broken limbs or losing a finger, and we could tolerate that once per 1,000 years. We're saying we can tolerate that severity once per 1,000 years. As things become less severe, we can tolerate them more frequently. As they become more extensive or extreme, we can tolerate them less frequently. So what we do here is we are going to go to our risk reduction factor. We have unmitigated or risk of this occurring of a loss of finger 0.4 times per year. We can tolerate it, once every 2.5 years. We can tolerate it once every 1,000 years. We need to reduce the risk by a factor of 400, and in this case, it would be reducing the frequency. So how do we take that risk reduction factor and then convert that to a probability of failure per hour so we can look at our tables as we have been? Well, we've got a probability of failure on demand of 0.0025 per year. So we've got a time frame of years there. Sorry, this should be 0.0025. Then we can solve for that, and it's 1 minus e to the minus lambda t, the reliability equation. And that's going to relate that we need a 2.86 e to the minus 7 failures per year is the target frequency or the failure rate we would need of the protective function to get us a risk reduction of 400. We would then look at our, that also falls into SIL 2. So that would work into this technique with the way we set up our tolerable risk gave us a similar answer. But one benefit of the LOPA is there may be more than 2 or 3 layers of protection you could potentially claim, and then you could clearly articulate them and document them in a LOPA approach. Now there are tools that can help do that. So there's process hazard analysis tools that we could document and do our entire machine analysis or machine risk assessment on, and we can do our LOPA where we're entering the data and the tool is calculating and tracking all those potential safeguards we need to have. Then essentially, once we have that, we need to capture that into a safety requirement specification. That's a critical document that's going to then serve as the input to the design and realization phase. With the SRS, we want to capture what really needs to be done. And the functional safety standards do a good job of stressing the importance of communication. Some studies have shown that 44% of the root cause of accidents come from improper specifications, either not understanding the hazard or not documenting what needs to be done. So the SRS is a living document, needs to be maintained and updated over time, especially the first time through as you're designing the systems, because you may put concepts down and when you first write the SRS that when you do the design, you find a better way to do it, or you find that the original thoughts couldn't be achieved. We should have machine information, risk assessment information, and target SIL levels into that safety requirement documentation. We're going to have functional requirements, which is basically what should the safety-related control function do, and we are going to have integrity requirements as to how well does it need to do it. So what risk reduction do we need to achieve, or what probability of failure per hour can we tolerate? What speed of response do we have? And then this slide here, this is a little hard to read, but going both through 62061 and ISO 13849, these are all the specific things that are called out to be in a safety requirement specification. So we're going to have, we'll make these slides available so you don't have to memorize everything on there. And then we ran a little long, sorry about that, but we have time for questions. So let's see. So here's one, how would you specify SIL or performance level from an e-stop, complementary protective measure? So in some, so in Europe, there's a requirement, and it's, what we're seeing is that that's typically specified as a SIL2 function, not specifically, there are requirements for the reliability and the effectiveness from some EN standards for a push button. So I've seen that like on turbine applications where in the hazard analysis there's automatic functions to take care of overspeed and other things, but then there's a regional requirement and expectation of a push button and the effectiveness of that. If you were going to claim the push button as a protective function, say in a LOPA, what you would really be doing is you'd be looking at that as an IPL, and you'd say, okay, here's my hazard. So what you would do is you'd go through that specific, independent, dependable, and auditable, and you'd say, all right, so if I'm going to have let's say operator A gets into trouble, and I'm going to have a push button for operator B to hit. So the first thing is you wouldn't say that the operator who put their hand in their machine is going to be in position to hit a push button to stop. Just from human reliability stuff, when there's stress, there's actually lots of studies, and that could be a whole different webinar, but on human reliability analysis, you still may want the push button there for the operator to use if they needed it, but you wouldn't typically give it credit because they wouldn't have time, they'd be under duress, so the reliability of the operator would be low. So in that instance, you probably wouldn't give it any credit. You might have it there as a good design requirement, and frankly, the machine standards are going to say you have to have it. Other option would be there is somebody else that could hit the push button, so you'd say, do they have enough time? Are they always there? Are they trained? Do they have enough time? If they did, then you could take credit, and then it would usually be the reliability of an operator, which typically is 1 in 10. So you'd say, hey, the push button might be SIL2 capable from a hardware perspective. Overall, the safety-related control function in this case requires an operator action, so we're going to take the hardware reliability of the push button and the operator reliability and add them together, and that's how you would determine what credit to take. So let's expand the questions. How much of the risk assessment should the vendor provide to the purchaser? I think that ultimately there's going to be, the vendor's probably in a good position to look at the typical hazards, crushing, burning, the typical machine hazards listed in OSHA and the other standards, and look at pinch points and those types of things. So they should be able to provide that. What they can't do is, without working with the user of the machine, is understand that machine in the context of the plant that it's going to be living in. So that has to that HAZOP really needs to be done looking at the site and potentially involving the supplier of the machine, but the user, the purchaser, really is going to need to be heavily involved in that. Is there a standard format for the safety requirement specification? No, there's not a requirement that of a certain format. The requirement is the information that is included in it or should be included in it. How do you get failure rates for different independent protection layers? That, I won't say it's a challenge, but that's something that needs good consideration and work. So There are guidebooks, there's guidebooks on human reliability analysis, there's guidebooks on, in the process industry, there's some good guidebooks from American Institute of Chemical Engineering that covers different types of layers of protection. Not all will be applicable for machinery. Then when you are looking at a protective system or different things, you can do reliability analysis and modeling of those systems to get it. And many pieces of equipment will have failure rates associated with them, so you can use those. We will get the slides to everybody. What documentation does the manufacturer need to supply? So that's a very good question, and this is a case where I personally find 62061 and 13849 weak. If you look at 61508, it does a good job of saying you have to provide a safety manual. You have to provide a manual that shows failure rates, gives guidance as to how to use the equipment in such a way to achieve that high reliability, what type of maintenance has to be performed, what's the useful life. That guidance is missing from, the machine application versions of the standard. So we really recommend understanding 61508 and 62061 or 13849 to be holistic. The biggest thing that I see as we work with customers, like even just trying to model the reliability, is OEMs will put out documentation and say, oh, we're performance level E with a failure rate of 2 fits. Well, there's other data there. We know a safety relay isn't going to only have 2 fits failure. That's not reasonable. It might only have 2 fits or failure per billion hours of dangerous undetected. That's reasonable and could happen. But ideally, the safety manual would talk about dangerous detected failures, configurations you need to do to be able to, say, claim category D or E, and provide good guidance. So those are things that should be considered by an OEM. What machines in the in the oil and gas industry typically undergoes safety review per 62061? What I would say, and say in oil and gas, a good kind of a place we often see both standards at least brought up is a turbine. Some folks out of Europe will say, well, a turbine's a machine, and you've got to apply 62061. Well, there are certainly, and what I say is for machine hazards, crushing, burning, pinch points, the hazard associated with a rotating shaft and somebody coming in contact with the shaft, the machine safety framework and those guide words and that analysis is applicable. For a turbine speeding and coming apart, or explosive atmospheres, those are process hazards. It's just like, and there could be a point of discussion to say, well, if the turbine comes apart, that's hit by something mechanical, that's a machine type injury. And I would say, well, you could have a batch reactor that you overpressurize and that comes apart. The process you're controlling in the batch reactor is a continuous, it's a batch process, it's a low demand type application similar to overspeed of a turbine. So the one thing that I've seen kind of cross over the machinery, or have at least that discussion, are things like turbines, pumps, moving equipment. So my guidance is to look at the guide words of the type of hazard and then decide, hey, is that a low demand thing that's better addressed by IEC 61508, or IEC 61511, or is that a high demand risk better addressed by the machine safety approach? This is a question about getting closer together between 62061 and 13849. I think I heard 6 years ago, 8 years ago, they were going to be harmonized and done in a year, and then talk to people who are on the committees, and they're like, that's not, we're nowhere close. So, yeah, I don't know that that's very close. I know they keep talking about harmonizing the two, but that's just a little bit of pain we're all going through. Does safety-related control function apply to machine monitoring systems like Bentley, Nevada, capacity control for anti-surge? See, I would say that that's likely, like vibration is more addressed by vibration surge. Those are more low demand SIFs. So if we think about it, we're going to be able to take credit for diagnostics. We're going to be able to take credit for proof testing. We're going to want to apply IEC 61511. So we are going to apply safety standards to it, but we're going to use the process industry one. Another question about B10 data often quoted for safety devices. Opinion on that measure. I think it's effective in finding wear out. It's ineffective in finding low demand application type failures. And the other thing is that there's a limit in 13849. So the B10 approach, sorry for those who may not know, is a cycle test approach where you test a sample till you get essentially 10% of the population fails, and then you extrapolate a failure rate from that. So if the primary failure mode is going to be wear out, and that's the function of that, then this is a valid engineering technique to predict that failure point. But you need to be sure that if that's the dominant failure mode for the safety system, it would be applicable. But the other thing is the safety standards 61508 says, hey, you need to determine useful life, and you need to replace all your safety components before they reach useful life. So it almost inherently says, you know what, we're not running these things to wear out, because then our failure rate kind of goes through the roof. So I think it's useful and very informative as part of the picture of how that device is going to work. You want to be sure it's applicable, and then also 13849 caps, let's say you calculated the mean time to failure of 2,000 years for the device and it was a sensor. I believe that, I know 13849 limits what you should claim, and I think it limits it to 200 years. So you might do a B10 analysis and you might get a really low mean time to failure, but 13849 is going to say, okay, don't use any more than this. So it's useful, but I wouldn't take it, I would take it in context. Oh, someone sits on that committee and can give me some background on the merger, so maybe it's closer than we think. That would be great. I'd love to hear about that. And then some folks who are doing some assessments, and yes, exida could absolutely help in that. So so I appreciate everybody for staying on longer. That's great. I'm sorry I try to be a little bit short, so I'm going to take a few slides out for this afternoon's version, but very much appreciate the comments and all the good feedback. The comments were very helpful, and we appreciate it, and stay safe, and we'll talk to you soon. Take care.